All right, so we were talking about classification. The idea is we would like to predict categorical variables. That's wonderful. We've noticed that there are a few nice categorical things that we use in our day-to-day life that we would like to care about learning to do ourselves maybe one day. So like spam prediction, it's just a classifier. It's output spam or not spam. There's no numbers there. Same with self-driving cars. Like your input is pixels, your output is like, oh, this pixel is part of another car, it's part of the road, it's part of a line in the road that I should care about, it's part of a stop sign, stuff like that. Also, input could be videos. Like, give me each frame is my input, where the ball is my output, and like you can map that to was it in, was it out. That's wonderful, and that's basic machine learning in a nutshell. We learned about that. So it's like you're teaching a computer to do something automatically. And the first algorithm that we learned, the one that we can figure out and do together, we're almost finished implementing it, is called the nearest neighbor classifier. It's like we don't care about what the data looks like. We just know that we've got a bunch of numbers that we can plot in maybe a multi-dimensional space. The goal is you give me like the attributes. We're predicting classes, like class 0, class 1, was there cancer, was there not cancer, stuff like that. You give me the attributes of an individual, like their hemoglobin amounts, their other things, blood sugar, I'm not sure. And we output like cancer, not cancer, chronic kidney disease, I think was their example from last time. It's like 1 or 0. Was it there? Was it not there? And the way that we're going to do the classification, the nearest neighbor algorithm, is it goes and takes the new point and it kind of plots it, like it draws a little dot, and it goes and finds the k nearest, because it's called the k nearest neighbors algorithm. It finds the k nearest spots around that new dot, k nearest ones. And so like if k is 3, we're going to find the 3 nearest dots in our training data, right? Because it's always there's always that concept of we're training our classifier with some data. We're going to save some aside to make sure that the classifier is not like accidentally guessing correctly. It's just like memorizing the training set or something. We'll have a separate test set. But like for a brand new person, go find the 3 nearest people near them in this multi-dimensional space with all these numbers that we're dealing with, like hemoglobin amounts, glucose amounts in like a blood test. Go find those, and whatever those were, like we have classes for those 3 dots, right? Maybe, where was it? We were here, right? We have classes for those. Maybe there was like the 3 nearest ones, we had 2 blue dots and 1 green dot, and we're just going to let majority rule. So you find the 3 nearest things nearest your new point, your new rainbow point, and if k is 3 at least, and you see what their classes were, and you use whichever one was most often, like blue, for example, in this case, and that's your prediction for that brand new person. All right, but there's a lot of math involved. We had to deal with distance calculations, like how do you find the nearest things in space? Like you're always like, for this new spot, compare it to everything else in our training set. Go find their distances using Pythagorean theorem, extended perhaps. And that gives us this. We kind of want a function that looks like this. K nearest neighbors. You give me the training set. You give me some brand new person. Maybe the person's name is Alice. And you give me the k value, like 3. Go find the 3 nearest things to Alice in the training set. Look at their labels. Give me the most popular label. That's our prediction for Alice. Does that setup make sense? There's a lot involved. Is it coming back to us? Because we're almost there. We are working on, that's where we stopped. We're working on k nearest neighbors on Alice. We've made up a little point in our space, and let's go back there. So yeah, we've got, I've imported that. Scrolling. We had like a pre-made example. We're gonna now do it ourselves, right? K nearest neighbors from scratch. So like here's our CKD table. We're gonna deal with hemoglobin amounts and glucose amounts and have those predict was there chronic kidney disease or not chronic kidney disease in a patient. And so let's pretend that Alice has 0 units of hemoglobin and 1.1 units of glucose. And the goal is to find, for everybody, calculate the distance from Alice to that person, Alice to that person, Alice to that person. We're going to do that for every person. So like the first patient in our data set was this one, like 11.2-ish and 117. We can do that distance calculation. We've figured that out, right? Take the x's, subtract them, square them. Take the y's, subtract them, square them. Take all that to the 0.5, so square root it. We're just doing Pythagorean theorem all day long. And we came up with a nice quick way to do that. Our distance calculation, you give me 2 points in space, represented as arrays. I can subtract them. That just subtracts their pieces. I can square them to get the square differences. I can sum them up, take the square root. That is our distance calculation. All right, so we've got a nice distance function that we could use from Alice to everybody else. Like right now it's just the one person from the top of the list, but we want to do that for everybody in our training set, and that's going to be the goal. So let's see. Let me import this table again. Let's draw a line. So let's see. We've got here's our table. Let's just redefine everything so that we don't have to like spend too much time doing all that stuff. So we've got our table. Here's our Alice again. Boop. Table Alice, and then our distance function. All right. So like those are the things that we have got so far. Let us now, our goal now is to find the distance from Alice to everybody. Okay. Does that make sense? That's our goal. That will give us k nearest neighbors on Alice. Boop. So I guess we can do that like this. It's like a subsection. K nearest neighbors on Alice. And k does not have to be 3. I think I'm going to use 5 as an example, just for fun. You can use any odd number, right? It can't be even, but odd is all right. The way that we're going to calculate the distance from Alice to everybody else is we're going to apply the function to our CKD table, which looks like this. We're going to apply a function to every, like these guys, just not the class part. So the way you can do that, the way you can quickly do that is let me show you something that I don't think I showed you more than once. It's like if you have a table, you can apply a function to every row all at once. Like you don't have to pick the individual columns that you're dealing with. So let me show that to you. So this is like a reminder that we may not remember. It's a little complicated. I won't test you on this idea, but you can do this. You can do this if you need it. You can apply a function to an entire table. All right, if possible, it passes each row to the function. If you don't want to do it this way, just like pass which columns are needed for this function, but you can do it all at once if you need the row. So let me just make an example table called T to show this to you. So let me have an X column and a Y column. And please shout out if anything stops making sense, like X's can be 1, 2, 3, Y's can be 4, 5, 6. Oops, that's got to be an array. And then there's my table T. So I've got a table T. What I can do, it has an X and it has a Y. I can make a function that takes, like when I apply it, it'll take the entire row by itself. So you can get individual rows of a table by saying like t.row index 0. And what you get back is not just like an array or anything. It's called a row object, we say. All right. So that's the type of it. The type is called, it's not int, it's not array, it's legitimately row, or the data science library. And you can apply a function to an entire row by saying like t.apply. You just give a function name. Usually when you say t.apply, you say apply that function to the X column and the Y column, stuff like that, right? You make a function that takes those things. But if you just say t.apply f, it's going to expect f to be a function that takes just one thing, that is the entire row at a time. All right, let me show that to you. This is how it works. So let me make a function called f, and it's going to take an entire row. I'll just call the thing row. And what it will do is you can say, like, let's say, because it's going to be applied to the t table. So it's going to get the x and it's going to get the y separately. So like index 0 of the row is going to be the x value. Index 1 of the row is going to be the y value. So let's just say like, all right, for that row that I've been given right now, let's just like add them up. Give me item 0 of the row plus item 1 of the row. And so like you're getting the pieces of it by extracting them, in a sense. Like you're given the entire row all at once, and that's how you can apply it. So if you apply just a function without saying anything after apply, after the name of the function, it's going to call this function with every row of the table. You're going to get it as one big chunk, and you got to go into and extract stuff out. Does that kind of make sense? So our goal is to apply a function like distance from Alice to the CKD table. All right, that's our goal. And it's easier to do it in this way where you just take the whole darn row. Much easier for us. So now let's do the same thing for our CKD table. I would like to do this, like take this table, CKD, and I'd like to apply like CKD without the class at least. Drop the class, that table, give me that and apply that. Apply a distance from Alice function to every row of that table, all right? So that's the function I want to apply. Def distance from Alice. Because we know who Alice is. We've got her in a variable. What we want to do is just like, all right, return the distance from Alice to this row as an array. And we learned how to do that last time. It's a little complicated. You have to say, you can't say make array out of it. You have to say np.array, give the thing. It'll convert the row into an array. That's what we did last time. So we need that here. So np.array from that row. So turning the row into an array. That's what we want to do. And so apply that. Say distance from Alice. We would like to apply that to like a row. Watch it work for an individual row. Let's see. To get just like one individual row out, like I can take this, give me row 0. So there's the row. I can apply this function to that row, and that's what's going to happen automatically when I do dot apply. So like that's the thing. That's going to work, and I just want to do that for everybody now. All right, that's how I want to do it. I want to say, all right, give me the table that has just all the things I care about passing to this function. So everything but the class from the CKD table. I want to apply the distance from Alice function. Go and do that, and there it is. So for every person, for every patient in our table, we've applied the distance from Alice function that took the whole row and compared it to how far away it was from our Alice patient. All right. So I've got all these numbers, and I can attach them into a new table now. Does that kind of make sense? What we've done? Any questions about that? It's like that's an interesting jump, and it kind of makes sense to want to do it that way. It's nice and generic, I guess, in that sense. So let's call this array distances. That'll work. Still there. And let's kind of like attach that to. Let's see. Let's attach that to a table eventually, but gosh, do I want to do that? Let's actually generalize this, because the goal is like you tried Alice, but you want to try somebody else after Alice, right? You got a new patient. You want to do this. You want to play this game all day long. So let's make a function that plays this game of like, all right, for somebody new, like give me the distance from that new person, Alice, now Bob, for example, to everybody else in the table. So like make a function on the fly that compares that new person to everybody else in the CKD table. All right, so that's what I want. And let me show you how we can get it. We can make a function, and it's going to look a little weird because we're going to put another function inside it. So let's make a function called all distances. All right, so the idea is we want to call it like this. So like, let's forget about what's going to go on. We'll deal with that in a second. Here's what I want to do. I want to be like distances not equals like all this weird stuff. Let's make it work like this. Distances equals like, let's not even have to worry about dropping the class. Let's just like have that work. And it's like we've got CKD and we've got this new person, Alice, right? I want to get all the distances from everybody in that table to Alice. That's what I'd like. I'd like a function that does that generates this for me, right? Because then it would work for any new patient, just somebody other than Alice, for Bob. I'll just do that for them too. So I would like this to work, all right? So let's see if we can make an all distances function that takes two things, right? Just generically, like here's our training set, if I can spell training set, and it gives me some new row, some new person that I haven't seen before, a new patient, for example, for this example, but it doesn't have to be for that. But our job is to do this exact thing for that new row. New row is Alice in our example, all right? So let's give it a doc string. What should it do? It returns an array of distances between each point in the training set. We really should have been good programmers and split up the trainings, like CKD the table, into training and test, but that's okay. Between each point in the training set and the new point. And yeah, the distances, the new point is just an array of all the attributes. That's the new word, right? Which is it's really just like a row maybe, which is an array of attributes, something like that. Which is an array of attributes. how do I want to say that? I think that's all right. Or let's just say it's a row. It's a row of attributes because then we can convert it to an array if it wasn't already. Let's do that, which is a row of attributes like glucose and hemoglobin values. All right, so that's what we want. And so what we'd like to do is compare this new row. What's the distance from that to everybody in the training set? We're going to do this game all over again where we take the training set, we drop the class from it. That's just the attributes only, right? So that's like, instead of this, you cut this off. We're just like, we're predicting this. Everything else is called our attributes that we're using to do the prediction, to drive the prediction, all right? So take your training data, drop the class. We'll just pretend that everybody knows it's called class with a capital C always. And that's the attributes we want to use in our comparisons. Attributes, everything but the class. And then we want to kind of do like, all right, return, give back our array, return attributes dot apply a function, like instead of distance from Alice, it's like distance from this new row. And so we've got some work to do in the middle there. But does that idea kind of make sense? It's like we've generalized what we did with this table. Like say Katie will be passed into here, Alice will be passed into here. Like for everybody, you got a training set, you got some new things, a new row of attributes. We want to compare all those existing attributes in our training set to that new row. So we'll make a distance function and apply it, and that will give us an array of a bunch of distances. Okay? You kind of see the vision there? So essentially what needs to go here is like this distance from Alice function. Like we need that, but it's got to be like distance from new row instead. And you can totally put a function within a function. It's going to be weird. Distance from new row. Because what does that need to do? Is like take, instead of Alice, it was the new row. And we're assuming that row might not be an array already. So we can say np.array, make sure it's an array by now. We can just do that. And like that's the function. And it's like using other things. So this is, you can make functions inside other functions. And we kind of need that here. They can use outer variables, which may seem a little complicated. Hopefully my copying and pasting and changing made it make a little bit of sense, but like new row was a parameter to this all distances function. We're just using it inside of here. It's like we're not taking it also, like new row. You don't need that. Like it already exists because it's part of the outer function in that sense. It's already defined. So this is our distance from new row function. I want to apply that, all right, which is, it creates an array of the new row and this current row that I'm given, and it goes and does the distance calculation for those two things. So it's like distance from this new row to everything that I could ever pass here. That's what I want to apply here. All right, does that kind of make sense how it's doing exactly what we did before, but in a generic way for any kind of data, any kind of training set? Because that's very complicated, I think, but the goal is that it's going to compute the same thing. All distance is not defined. All distances, excuse me. All distances. It should be exactly the same now. If I print it out really quick. Distances. The last one was like 130.85. 130.85. Yeah. So it's still there. Are there any questions about how I came up with this function? Do you see its goal? It's like you give me a training set, you give me a new person in that training set that may or may not already be an array. I'm going to calculate the distance from this person to every one of the rows in this table, the attribute parts, the things that don't have the class. It's all the numeric stuff that we care about using in our distance calculation, all right? So you can make it a function within a function. That's the one we wanted to apply. The distance from that new row to some other row that I have in this table. I'm going through all of them. Row gets to range over all of the rows in this attributes table that I'm generating, all right? So there's a lot going on there, but I hope it makes a little bit of sense. Yeah. So that's fun. Let's see here. But now we can do what we're setting out to do. It's like CKD, give me that table, but let's add the new column, like distance from Alice now. With a column, distance from Alice, and that's going to be our distances array that we worked so hard on calculating. Look at that. So for every point now, we kind of disregarded the class. It didn't matter. It's like we know the distance from this point to Alice, and it was that. The distance from this point to Alice, which was that. For everybody, we got that now. And so let's call that something, CKD with distances. This is very technical today. This is a very technical chapter. There it is. And I want to do k nearest neighbors. I want to get the top k, or sorry, top k in terms of shortest distance, right? So I want to sort this table based on this column now, don't I? That's the next step. I want to get the things with the smallest distance to Alice, because that will tell me I just take an odd number of those that I use to drive my calculation, to do my prediction. So I'm going to sort it. Sort by distance to Alice, or distance from Alice. Doesn't matter. Just sort by distance from Alice. I get this table. And I guess it depends on what your k value is. If your k value is 1, you're going to predict class 1, aren't you? So you take the top one thing. If your k value is 3, we're going to predict 1 because there's more 1s than 0 in the top 3. Yeah. If our k value is 5, then it disagrees. Ooh, it's going to predict 0 instead of 1, isn't it? So, I mean, we don't know what Alice has, or like whether she has this disease or not, but you can see that it kind of depends. The more data usually is going to help you, but there's also, it gets farther and farther away at that point. So there's some diminishing returns, I guess, is what you should say. But like if we're going to program this, like, all right, to do a value of k, let's pretend that our k is 5. So I want the top 5. That means after the sorting process is done, I want to take just 5 rows now. So I can do dot take, give me 5 things. So indices 0, 1, 2, 3, and 4, right? So take all the things in this array, np.a range up to 5, which is going to be 0, indices 0, 1, 2, 3. That's going to calculate that array of indices that I care about. And there's my top 5, if k is 5, for example. All right? We're so close. We're so close. Let's pause, because again, we want a full program that will do this for us. Let's pause and make this more generic. So you give me Alice, you give me your training set. I want to get like the 5 nearest things to that new value. So I want a function like this. I want a function called like nearest that takes our training set, it takes the person that's new that I want to find the distances for, and like the k value as well. Like I want that to produce this. Does that make sense? I want something like that. Give me a function that works like this, then I can make this generic for any kind of training data. So give me the things with a class, go find the distance from this Alice person to everybody else, give me the top 5 in terms of smallest distance. All right, so let's make that happen. That will generate this table. That's how I want to call it. I want it to generate that exact table. So let's do it. So yeah, I guess let's work backwards. Nearest. So you give me a training set. You give me some new point in that training that is not in the training set that we haven't seen yet that we want to classify. You give me a value of k as well, and I want it to return that table for me. All right, so this is going to returns a table of the k rows corresponding to the k smallest distances. All right. Returns a table of the k rows with distances attached, right? Let's say like having the k smallest. Having the smallest distances from the new point. Something like that. Does that make sense? That's what we want it to do. That's describing this process. Returns a table of k rows with distances attached, having the smallest distances from the new point. Okay? So yeah, that's kind of what we want to have happen. Let's see. What's the best way to do this? So let's make I guess we need to run this again, right? We kind of want to, let's see. Almost, at least. We want to do this process, yeah? This function that we did, like all distances. Give me all those distances and make a table based on those. Like that's our attached thing. So give me all the distances, distances to new point, something like that. And that's going to be all distances. Oh, goodness. Why is that not defined? all distances from the training set to the new point. So that's going to give me an array of distances, right? From the training set to the new point. What are all their distances? And then I can make a table, right? That's what we did next. Make a table where we attached a new column, training set with all the distances to that new point. I'll have to do that attaching. So this can be like with dists, that's the table, equals a, like, it's our training set with a new column that we can call, let's just say like distance. And it's going to have all those distances to the new point. So that has created this big long table that's out of order, right? Now we got to sort it. And please stop me at any point. This is very complicated. This is technical. So then we want to sort it. So like sorted by distance is you give me that table of all the distances, the with dists table, and you sort it by distance. And then I want the top k. Yeah, I want the top k values in that table called sorted by distance. Give them to me. And so that will be my nearest neighbors table. That's you take sorted by distance. You give me the top k values. So dot take indices 0, 1, 2, all the way to k minus 1, like 0, 1, 2, all the way to 4 for 5. np.arange with k. All right, and then return that. Boop, boop. Oh. I have forgotten to do something. Oh, that'll do it. So I think that did it. So I've made this function that generalizes this process. So now it's just like, we can use this for everything now. It's like, you give me the training set, you give me some new person, you give me the k value, I'll give you a table of that many things with the smallest distance to this new value. So yeah, that's most of the way there, yeah? We've abstracted it all into this function that calls our other functions that we've made. Are there any questions about how this is all working together? There's a lot going on, I know. So, all right. The last step is we're just going to assume always that it's always capital class. Like that's the name of the column with the labels. And we want to do majority rule now. All right. Take a majority vote of the k nearest neighbors to see which one have appeared more often. Was it zeros or was it ones? And that's our guess. That's our prediction. That's our classification for that new value. Okay. So here's kind of how you could think about that. Like just like you got this table. Use table stuff. Like figure out how many ones are in this table by like taking it and like extracting, like do a dot where the class was 1, dot where the class was 0, right? Let's do that. So like let's call this table something like 5 nearest neighbors. Is that? Because I want to use it now. There's my 5 nearest neighbors to Alice. And all right, I want to see how if there are more ones or more zeros programmatically. So I can do this for a bunch of people. It's good to go. It's like, how many ones? What are all the ones in the table? Just like take the 5 nearest neighbors, do a dot where the class values, and you could just say 1 here, but you could be like r equal to as well. R equal to 1. That would give me the ones. What could I do next to figure out like how many ones there were? So that's a table of just the ones. How could I get how many there were? I could count how many rows. Yeah, good. I can be like that, dot num rows. That's how many ones there were. Yeah, I can do the same for the zeros. Ones are those. That's how many ones. This is how many zeros. Is it zeros with an E, maybe? I can't remember. Something like that. And then, that's going to bother me. I'm going to search. What is 0 plural? Is it zeros or zeros with an E? The most common one is without an E. So like instead of potatoes, I guess people do that instead. Now I know. All right, so the question is, which one was more? We're going to find out that zeros is holding the number 3, right? And ones is holding the number 2. And so I think an if statement is probably the right way to go here. So like if ones is bigger than zeros, then I guess like we can say print, for example, like print 1, otherwise print 0. Because if this wasn't true, that means you used an odd number, right? So that would imply that it was less than, ones was less than the zeros. And so that's kind of the game. You make this table, you do this calculation, and that is our guess for Alice. That's our classification for our point called Alice, our new patient. We compared her to everybody else in our training set, all of our attributes. We were predicting her class based on the 5 nearest things. We call it with 5, right? The 5 nearest things that looked the most like her in our patient training set. And it just so happened that there were more people with class 0 than class 1 for those 5 nearest things to her. And so we're going to predict class 0 for Alice, when k is 5 at least. Yeah? Any questions about that? Yeah.
If the zeros happen to be like way far away, even though they're the majority, would we still want it to be 0?
Then you should be looking at like some sort of scatter plot to see like how far were they away? Is there a big cutoff maybe? Because that will definitely tell you. If that's true, that kind of implies though, if that were true, let's think about that. Because that is for sure something to consider. Like here is, I don't know, just for a second, like here's Alice, and like here's really, maybe there's like one person over here, another person over here, like everybody else is way over here, so that's kind of what that implies, right? So it kind of implies that Alice was an outlier to begin with, and so maybe your data can't predict her well in the first place. You see that? So that might say that your data is not great, and you might not want to use k-nearest neighbors on Alice. You might want to like go get more data or something like that, or check your measurements, because the whole point of k-nearest neighbors is you want to find people that are nearby, and if there's not a lot of people nearby, this is probably not a good algorithm to use. That's a great question. Does that make enough sense? Yeah. Other questions? Whee! So yeah, emphasis on the nearest. If there is no nearest, then you're kind of out of luck. Whee! All right. So we're pretty much all I would like, right? What I want is a function that you give me the training set, you give me a new person, you give me k. It prints 0, right? That's what I want. Now they'll do everything for us. So let's make that happen. Let's generalize this process of like figuring out who's the majority winner. The majority, you give me a nearest neighbors table. I'll do the majority calculation for you. It's like just that, right? And we'll have it, instead of printing, we'll have it return. Return 1 if there's more 1s than 0s. Return 0 if there's more 0s than 1s. If it was an odd number at least. So like we can call that now, like call majority on our 5 nearest neighbors table. That will predict 0 for us. And so that brings us finally to this idea. We can finally do that. We can finally make a function. You give me a training set, you give me a new person, you give me a value for k. I will do the k nearest neighbors algorithm to predict my best guess of the class for this new person. We'll do it. I would like something that works like this. You give me k nearest neighbors, you give me the training set. Let's just say it's the whole table for us. You give me this new person, this new point that we want to predict stuff for, and you give me a k value. How many people do we want to find nearest to that person and take a majority vote for? Let's make that function. Are we ready? Pretty much you just call majority after calling nearest. Yeah? We've made all this, that we've set it up for ourselves. Def, you give me k nearest neighbors. All right. You give me the training set. You give me some new point in that training set. You give me a k value. I will find the nearest neighbors to that point by calling nearest, just like I did here. It doesn't have to be 5 nearest neighbors, like that's our nearest neighbors table. We're generalizing this process. Nearest neighbors table. The nearest things from the training set to the new point for whatever k value you wanted to use. All right, that's the top k. Then I want to do a majority vote over that top k. Yeah? And then return back the majority class label in that nearest neighbors table that we've generated. Does that make sense? It's like we're handing off the problem to functions that we've made. They're handing off themselves, their problem to other people. But that lets us, once and for all, have just a function called knn, You give me a training set, you give me a new point, I will compare that point to every value, all the attributes of every row in this training set. I'll find the top 5 in terms of smallest distance. I guess I'll find the shortest distance, the shortest k things, the shortest 5 things to this new point. The closest, I guess, is the right word, right? The closest 5 things. I'll take a majority vote over those 5 things, and the predicted class for Alice is 0. I have a function that does it all now. That's lovely. Are there any questions about how all these functions are playing together nicely with each other? Well, we started with what? The distance function. So the distance function is being called by this all distances function that's going at, like, you give me a new row, it's comparing it to every value in the training set after dropping the class. We're getting all their distances. We're attaching that in the nearest function, like you give me the training set and the new point in the k. Get all the distances, attach those as a table so I can extract the top k. That's us doing that. And then do that, take the majority vote over the classes that you see. You've got k nearest neighbors. That's the algorithm. It's so cool. We did it. Any questions about that? Do we see it all working together? It's going to take, maybe you want to study this and have it sink in, but like that's the setup. It's doing it. It's actually doing it. So it's a lot of stuff, I know. Question, yeah. Yeah. Oh, thank you so much. Yeah, that's an error. That was an error on my part. It should have just been the nearest neighbors table. I did not generalize it properly. Thank you. So it worked because we're still working on Alice. But if it was somebody else, it would not have worked. Very good. Thank you. So yeah, please yell at me if you notice anything like that. Anything else that we see? Yeah, so you always want it to work for your parameter for sure. Thank you. All right. Yeah, so I've got that function. It's happy. I think I've generalized everything else down here. But yeah, you give me somebody new, like we'll find their distances. That's how it works. You make a Bob now, and you can have it play nicely. All right. Are we ready for a completely different example? Just doing it from start to finish. We have the functions now. We'll watch the functions work in the same way. It's going to be great. All right. So let's do, this is a new section maybe. K nearest neighbors. It's an example for wine. Because apparently you can get a lot of numerical values to like, on different wines, and it kind of like the values, they're all the same for certain kind, like Pinot Noir is a certain kind of, like it has a certain alcohol content, it has a certain other things, and so you can guess stuff. So first, before we get to this example, I want to show you and just prove to you that our distance function works no matter the dimensions. It's going to work for anybody. This is our generic distance calculation. Like you just do it for as many attributes as you have. You just do the x's, the y's, the z's, the p's, the q's, any things that you have. And you subtract them, you square them, you add them together, you take the square root. That is the distance calculation for any dimension. And so let me show you. Let me just prove that your distance function that we've made, it works no matter the dimensions. All right, it's going to work for everybody. So let me just copy and paste our distance function because we're thinking about it right now. It's already been defined though. Here's our distance function. And there it is. And so watch. I can say distance. You give me an array of like 3 things. 1, 2, 3. Give me another array of 4, 5, 6. And it's comparing the point 1, 2, 3 in 3-dimensional space to the point 4, 5, 6 in 3-dimensional space. It's still happy. It can still do the distance calculation because this is going to work on everybody. Then you square them, then you sum them up. It's like that's the right calculation for everybody. It's going to work for 20-dimensional data. Still is fine. Okay, so the distance function is golden. It is okay. And so with that, let's import the wine data. Table, read table. It's in data/wine.csv. And here they all are. Let me do a sample 10 things. Show you that there's other classes involved here. Like these are different kinds of wine, apparently. They have different alcohol content, different whatever that is, different ash content, alkalinity, different amounts of magnesium, maybe in milligrams, just kind of like cereal in that sense. But you got a bunch of different values for different wines. And you better believe that we could make a classifier based on, you give me everything but the class, we can predict the class of wine, what kind it was. I don't know what the number represents, but probably look that up somewhere. we have been focusing on, like, was it one thing or was it another thing, like a binary classification, only two things. There are multiple classes, there's at least 3 classes, it looks like, of wines in this data set. Let's just focus on class 1, predicting, was it class 1 or was it something else, was it some other class? So just briefly, let me modify the table. Let me change all the 2s and the 3s to 0s. That's what I'm going to do. Okay, so we'll focus on class 1 versus the rest. So I'm just going to be like, I'm going to make a function really quick just to make that happen. Like, is it 1? You give me a value, I'll say if it was 1 or not. So if x is 1, return yes it was 1. Otherwise, else, I'll turn everything that wasn't 1 into 0. That's what this function is going to do. I'm going to apply that to the class column. So line with a column. I'm going to replace the class column with that. Of you saying line.apply the is1 function to the class column, to class column number 0 of the wine, the original wine table, put that right back into the wine table. So I've just turned the wine table from a bunch of, let me do another sample. And I'll have to do this again. Boop, boop. There we go. So I've turned the wine table into a bunch of 1s and 0s now. Like the 1s were the same, and if it was anything other than 1, I turned those into 0. So we're going to predict, was it type 1 of wine or not? All right, so it's a binary classification. That's what we're going to do. And yeah, let's explore the data set a little bit, and we'll do the same game. Do the same game for on these different wines. So, all right, our attributes of the wine is everything but the class. We want to use all these attributes as numerical things to predict what kind of wine it was. Okay? So that we can call our wine attributes. That's like the wine table, and you drop the class. And so what we can do is we can compare, I can show you that our distance function, like it shows a small value for wines that are kind of the same. Let me print out the whole, like the start of the wine table. This is like this is row number 0, this is row number 1. They're both class 1 of wine. All right, so let's do the distance calculation on the wine attributes table, row 0, as an array, because distance only works as on arrays. Take that and compare it to row 1 of wine attributes. That's everything but the class. All right, and these are both class 1. All right. Boop. Oh goodness, sorry. 0 to 0, of course. There's 0 distance between them. 0 to row 1, though. That's this wine compared to this wine, dropping the class. Comparing all these other things to each other, putting it in like a, I don't know, 10-dimensional space, I guess. All these are points in a 10-dimensional space that's comparing them. Does that make sense? It's giving, they're 31 units away in that weird space. All right. And so the distance function, it's comparing all of these things, everything from alcohol onto proline, whatever that is, if that's how you pronounce it. So it's just working for us. The distance function is doing like 10-dimensional distance calculations. It's comparing a ton of values all at once. And it works. It works just fine. All right. Let me compare this to, like, that's the calculation between row 0 and row 1. Those are both class 1 of wine. Let's compare it to a class 0 of wine to like prove to ourselves that k-nearest neighbors is a good idea here. So wine.row, give me row 177. Apparently that's a good one. That's a class 0 wine. It wasn't class 1. Let's compare row 0 to wine 177, which is the, I guess it's number 178 really, because you started counting at 0. Boop. And so this is us comparing class 1 versus class 0. Do you see that the distance is much farther? So that's kind of telling us that, okay, maybe a distance calculation is a good idea. K-nearest neighbors can probably predict wine class as well. That's nice. Good to know. You can also make graphs of that. You can do a scatter plot of at least 2 of these. You pick your favorites. Line.scatter. Apparently a good one to do is flavonoids, however you pronounce it. Please correct me if I'm not saying these words right. I'm not a wine connoisseur. Alcohol content. Compare those 2 things, and if you group by, you can always say group equals what you want to color it by, group by the class, you can see that that's kind of like, there's kind of a line there, but there is still a bit of overlap, so like, it wouldn't quite work. Distance calculations using just these two because there'd be some overlap there. So you might as well compare all 10 different things all at once. And other ones, they also have some overlap. Like, apparently, alkalinity of ash, whatever that is, to the ash content. Again, those kind of separate the different kinds of wines, class 0 from class 1. But again, on the middle parts, there's some overlap. So like, no two attributes are doing a great job here. Same with like magnesium. So you'd be exploring this data set and noticing this. There's nothing that can separate it perfectly. No two things, no X and Y. Total phenols. That's how you pronounce it. Again, there's a decent cutoff, but there's some things in the middle. So the idea is we see that there's some separation between different variables, but there's still a lot of overlap. Lots of overlap. But multiple features or attributes at once. Another word for attribute is feature. A bunch of features at once, rather than just two, like we've been showing in the scatter plots, 2 at a time, can usually make it happen for us. Because it's like, these ones in this overlap were different than these ones in that overlap. And so if you combine them all, we're happy. Okay, so that's what we want to do. We have functions to do that for us. Let me show it to you. So remember that wine row 0, that was wine that was class 1, and all those numbers. Let's do a k-nearest neighbors. This is not quite k-nearest neighbors because I have not made a training set. I'm just going to show you our function working again. It's our nearest function. Nearest function on, give me the wine table. Compare it to, I guess it's not wine row 0. We want just the attributes only. So we've called that table actually wine attributes already. So that's nice. Whee. Compare it to wine attributes row 0. And give me the top 5. Give me the nearest 5 in terms of distance. So here, that's what happened. So wine row 0 is this guy. We're comparing this thing that's actually in the table, to everyone in the table, give me the top 5 in terms of lowest distance. And so if we scroll to the right here, you see that it's found itself. That's distance 0. Like that's the original wine. It was distance 0 from itself because it was this was part of this. Yeah, it was there. You see distance 0, so that kind of doesn't count. But you see a bunch of others that are close by in terms of distance calculations that were all class 1. You see that? So that's showing us that, all right, this one is near other class 1 wines and not any other class 0 wines. That multi-dimensional distance was doing a good job. It was not overlapping zeros and ones. See that? That's lovely. That's good to know. And same with the wine at row 177. That was a class 0 wine. If I do the nearest calculation for that one, boop, you better believe it's going to find itself again, because it was part of the training set. You should have split it up, really. But here's a bunch of other close wines in terms of distance. And what do you know? They're all class 0. So there was no overlap when you use that many attributes, that many features all at once. Does that make sense? That's telling us that nearest neighbors is doing a good job, and we can maybe make a wine classifier. Okay? So yeah, if that makes sense, that's most of the story. The job of us now is to see, like, all right, that was the process. Let's actually see if we did it good. Let's see if this classifier that we've made will save away some stuff as a test set and compare it to, like, we'll test all those things using our training set for getting the labels. Let's see if it actually does it properly. If we save a few things, is it just memorizing? We'll find that out. So that's our goal. So like, we want to use our training set to predict. This is how you evaluate if it was good. You save away some stuff in your test set, things that you've never seen before, and you kind of like forget about what class it was in. You send it to your classifier. Send all these to k-nearest neighbors. It predicts a bunch of classes. It thought it was this class, this set, this set, that set, that set. And then you compare against the original ones that you didn't tell the training set at all about like, all right, were these ones here, were they equal? Question mark. Does that kind of make sense? That's what we want to do. Like we've never seen these before. They weren't part of the training set. For each of these features, each of these rows, use the training set to classify it, and we can use the original classification that we know it really had to compare. All right, that's how we evaluate. So use the training set to predict every individual, every patient or whatever, every wine in the test set, and then yeah, that's how you do it. You want to split up in a way that you know like you've got a good amount of each. So like a random sample would be a good one. Like shuffle it all and then do a split. So both of the training and test sets better accurately represent the population. They better be good. Otherwise, if you got nothing but class 1s in your test set, then you forgot about how well it's gonna like predict class 0. Otherwise, that would be a problem. So like make sure it's a good amount. Shuffling the data is usually fine. And what you're doing by doing this is preventing what's called overfitting. That's when your classifier, it works really well on just the training set's data, but it has no clue what's going on when you feed it stuff from the test set that it has not seen yet. That's kind of implying that it's memorizing the training set rather than memorizing like what different wines look like or what it means to have chronic kidney disease. All right, there's a difference. I hope that makes sense. So memorizing rather than learning, because this is machine learning. So that's our goal. We want to send every element of the test set. We'll save away some stuff, send every piece of it to our algorithm, get its prediction, and compare it to the actual things that we know the classes were for that test set. Okay? That is evaluating the classifier's accuracy. That is our goal. And so yeah, it's just a lot of me showing you stuff today. Eventually, I'll have you try some stuff. That's our next example if we can get there. All right, so okay. We would like to split up our wine data. All right, so wine. How many rows are there in wine? No, rows. We've got 178 things in our wine data set. What is 178 over 2? 89. All right, so let's take the first 89, have that be our training data, and the second, like another 89, have it be our test data, but not actually, and when I say that, I don't mean just take the first things in the data set and compare them to the second things in the data set, because in the wine data set, it's a bunch of class 1s to begin with. So what we should first do is shuffle the data, then take 89 things, the first shuffled 89 things, and then take the second shuffle 89 things. One's training, one's test. Does that make sense? That's what we can do. Then we've got a good amount of 0s and 1s in both of those. Okay? So, we better shuffle first. But like we know the amounts now. All right. So, shuffled wine is you take your wine data set, you sample it with as many things as you had in there. You can just say, I guess you could say 178 or whatever it was. But you could also just be like, nothing, with replacement equals false. Take as many things as there were. Do not like duplicate anything. Keep as many things as there were. Just shuffle it around. That's what that means. And then we can make a training set from that. We can take the shuffled wine stuff, and we can take the first 89 elements. So indices 0 through 88. Take these indices, np.a range, up to 89, so 0 to 88. And then the test set is everything after that. Indices 89 onwards to, I guess, 177. So you can just, as easily as he said this, be like, all right, starting at 89, then going up to 178. And that's kind of why this was made in this way. So you can do something like this. Like, you keep the same number twice. This one doesn't go up to 89. This one starts at 89. That's kind of why they made that that trade-off. So go up to and this go up to as many as there were, but 177 is the last index that will be calculated there. So that's going to be a perfect split of the training data, of the wine data into a training set and a test set. So I have a training set now and I have a test set. Does that make sense? It's part of it's shuffled. So like the training set, you can see it's got a bunch of different things. It's got a class 0 stuff, and it's got class 1 stuff in it, and so does the test set. They all got those. And so we want to test everything in the test set using the training set. Okay, that's our goal. Using training set to predict every individual in the test set. And So for every individual in the test set, we're going to get a prediction, and it will be class 0 or 1. We're going to apply a function, essentially. And so what we're going to get back is a big, long array of a bunch of 0 and 1 predictions, right? A bunch of 0 and 1 predictions for our test set. We want to compare that to the original classes that we've saved away for our test set. We know what they really were. We're just predicting them just to see if our classifier is doing well. And so we're going to end up with 2 arrays, essentially. Our predictions and the original classes that the test set actually had. And we want to kind of see if they were the same. And so remember that you can use equal equals on arrays to do that. And it'll get back true, false, stuff like that. So remember that you can do that. So we can use equal equals on arrays to test the original classes against the classifier's best guess for the class that it should hold. Okay? So get a bunch of trues and falses, and you better believe you can count non-zero those. Just be like, all right, np.count non-zero, all those values, and you kind of divide by how many there were to get like how well it did. So 66% good classifier. You got those values back. All right, does that kind of make sense? That's what we want to do. So our goal is to, you give me, this is how it's going to work. I want to say something like this. I want to make a function called evaluate the accuracy. You give me a training set. You give me a test set, and we have 2 of those. You give me a k value, because we're doing k nearest neighbors. You need to say what k needs to be. And this will give us back like how well it's going to go through every piece of the test set, evaluate it using the training set, try to predict using the training set for that new row each time, each value in the test set, using 5 nearest neighbors, I guess. And we'll just see, like, did it do it right? How many times did it do it right? That's my eventual goal. I want this, all right? Goal, make this function. That it'll work and give us back a value, all right? So let's just like do it simply first. Like, all right, we've got a test. We've got a test set right now. There it is. We want to compare every attribute of this, like every row of this, dropping the class though, like drop class. Compare every attribute of the test set to the training set. So like, we'll call this test attributes. All right, so I've got all the things, everything without the class. And what I want to do is, I don't know, gosh, the best way to say this is just to do one example, I think. Like, all right, go through each of them, like test attributes row 0. Like that's the first one. Go and compare that, right? Go and compare that to everybody. So like do a k nearest neighbors on the training set, using the training set to compare. Compare against, like that's our new person. It's just the first row of the test set. We're going to do it for everybody in the test set. And like let's have KB5 or something. And our prediction of the class for this row 0 of our test set is 0. And then we go and we compare. Oh, was it actually 0? Yes, it was. We did it right for that one. Does that kind of make sense? What's going to happen? We're just going to count like how many times we did it right. Like this is our prediction. Because we dropped the class. This is our prediction for row 0 of our test set. We're going to do that for every row. All right, I'm going to do that for every darn row. And so we essentially want to do this. We want to do, all right, we want to take our test attributes and we want to apply a function more or less, like apply a function like do k nearest neighbors on that thing, on that row now, something like that. We'll call it like classify this test row, so our test data is a row. Let's make that function. So def classify test row. You give me some new row, because we're applying a function to an entire row, right? And we want to give back our prediction of the test set's answer for what this row's class should be. So like do k nearest neighbors using the training set on this new row with k being 5. Something like that. Return that. Does that kind of make sense what that's going to do? And so it's doing a prediction. It's doing a prediction, and I maybe messed something up. We'll find out. But like that's what it's doing. That's what it's predicting for what it thinks that each value should be. Like was it 0? Was it 1? Okay. You're going to get back a big long array of a bunch of ones and zeros potentially. This one, it looks like it has all zeros, so I maybe messed something up, but that's kind of the idea. I want to apply a function, so for every piece of the test data, we want to classify it using our training set, this brand new row, do KNN with like 5. Okay? Questions about that? You see how it's going to work? You just want to see how many times it did it right. It's like, all right, compare that, because we know what the classes were, right? We know what the classes actually were. Compare all these to the test set dot column class. And sometimes it'll be right, sometimes it'll be wrong. Does that make sense? Sometimes it'll be right, sometimes it'll be wrong. How often was the question? And so we can do like a calculation like this. Like do that, np.count_non_zero. All these things divided by the size of the test set. Test set numbers. There's our calculation, and it's like 64% accurate or something. That's the goal. Okay, does that kind of make a little bit of sense? That's what needs to happen, and it looks like we maybe got a bad split. If we had a different split of training and tests, we'd get different answers because it's going to use a different shuffle of things. If I replay all this, a new training set, a new test set, that's still all fine. Test attributes, still more or less the same for that one. And this time, if we do that, we get about that much accuracy. So that's interesting in itself. So I think that's how we want to do it. And so, again, our goal is to make one big function that does it all for us. Evaluate accuracy, you give me the training set, you give me the test set, and a k value, and it will all work out. Okay? That's what I'd like to do now. So, with that in mind, let's kind of generalize everything we just did. Dun, dun, dun. So let's see. Yeah, so we'll do def evaluate accuracy. You give me a training set, you give me a test set, and you give me a k value. We're going to give it that one. Our actual training set, our actual test set are 5. And we want to give back like how well did it do this counting. So the process is going to be give me all the attributes, give me the test set without the classes, because that's what we're going to compare against. So I'll call that test attributes. You give me the test set and drop the class. And yeah, we'll say classify. We want to then apply, right? We want to apply our function, like classify test row, to all those attributes and do that calculation. So I guess let's put this in here. And I want this function. I want to apply a function like this to everybody. Let me change it in a second. And like that is going to be all the predicted classes. I'll call that C. Predicted classes is you take your test attributes and you apply the classify test row function to it, where for this new row, compare it to everything in the training set, which we've called training, and use the same k value. So this is like a function within a function, so I can keep that k value, essentially, using all those things. So I think that's what I wanted to say there. So there's the predicted classes, and then our job is to give back, comparing those predicted classes to the actual classes in our test set, because the test set actually had classes still. And so it's this idea. We return that. It's going to be a little disgusting. So return count non-zero of, hey, were the predicted classes equal to the actual classes? And it's not test set, it's just called test in this function. We're calling it training and test. If the predicted classes are equal to the actual column called class divided by test.numRows. And that is our evaluate accuracy. I think that is everything together. And we get a value, then that's the same value. Any questions about that? Do you see kind of how it's working? It's taking every element of our training set, we're predicting it using our classifier, we're taking every element of our test set, predicting its classification, using the training set to do the nearest neighbors calculation, using the same k value, and like we're keeping track of, was it class 0 predicted, was it class 1 predicted? Yeah? And that gives us that. I do think I have an error somewhere, though, because I'm getting a value that's a little too low. I think I saw that it was always predicting. It was always predicting 0 for me, and I think that means that I accidentally did not use a variable when I should have in a function, so I'm going to have to go back and look. But I think, yeah, like this one, if I, for a second, get rid of that, if I say, just give me the answer back, it looks like it's always predicting 0 right now, and it shouldn't be. So let me try to figure out why. Because they're all different. They are all different. So I think it's one of these functions. So if you can help me scroll back and figure it out. It's like, all right, that's the wine table. That's not the problem. I think it's one of these. Nearest neighbors, I think it may be majority, because that's the thing that's giving back 1 or 0. Oh, there it is. See it? I forgot to see, was it equal to 0? There we go. So it was always predicting 0, it looks like. And it doesn't change Alice, but I think it's going to change everything else. There we go. So that was my error. Whee! So still scatter plot did not change. Line row 0, row 177. I think we are in business. Class 0 is still the first thing. That's great. Test set. Also start with class 0. Whee! Predicting class 0. Yeah, we got some trues and some falses, and I think that when we apply it, it's now sometimes going to say 1 and sometimes going to say 0. There we go. That's how it should be. Okay, good. So I was doing a bad version of the prediction. It was 91% accurate for this one, for this split, and we should get that again by using this function. Okay, that makes me happy. All right, that's how it should be. It will be different. Like it was a random split of our table. So if I ran this again and I did another shuffling, I might get a better accuracy or a worse accuracy, but it would hover around that number. All right. So what we're doing is we are using our training set to predict every class in our test set and hiding the class of the test set secretly aside until the very end. So we get our predicted classes by using the training set to predict every value of the test set, predict those classes, compare them with the actual classes that we had saved away. We didn't tell the k-nearest neighbors algorithm about. We knew what they really were. We saw how often did it actually do it right. It was 91% often. That's great. Yay. So that is how we can do it. Now we have a function just immediately. You make a training set, you make a test set. We had no clue, like, were there just 2 things? Was it glucose and hemoglobin? Or were there a million things, like for the wine? This will work for each of them. You give me a k value, and it will evaluate that accuracy. We could do k-nearest neighbors of 3. Like, was that better? No, it's about the same. K-nearest neighbors of 1. That's going to be a little bit worse. It's just like predicting the one closest thing. So usually a little bit is better, but not too many, maybe. Yeah. So that's how we can test, was our classifier doing a good job? We save away some stuff secretly. We predict each of those things, seeing how our classifier did, counting how many times it did it right and did it wrong. That was a lot to talk about. That was just one slide. Man, any questions about that? You see how it's working together? We made a bunch of functions. They're all happy, but they're all a little complicated. I've tried to abstract away the problems, though. All right. So I think with that, are you ready to try it yourselves? So let me give you all of this code right now that we worked on. That's important. So if you go to any other code from class page or just the one by default, you can now, if you refresh it for chapter 17, you will have every single thing we've done today so far. It's all in there. So I'd like you to go, oh wait, maybe not actually. I need to click save. Let's say now you do, just in case something changed. So refresh it. Yeah, refresh it once more, sorry. There you go. So you've got everything we've done today now, and I have a new training and test example. So we've got a data set from the textbook on breast cancer, and let's take a look at that data. It's called breast-cancer.csv. It's that file. Let's look at the data together, and then I'll have you train and test let's do 5 nearest neighbors. K-nearest neighbors with k equal to 5, and see how well it did after doing a split yourself and doing it all. Okay? So that's breast cancer example. So let's read in the data at least. It's a bunch of patients. I'll call them patients. Table, read table, breast cancer.csv, and I'll show you a few of them, like sample 10. We want to compare them to each other using things that are capable of being compared. Clump thickness, uniformity of cell size, all these numbers, things. The ID number was like an anonymous form of the patient's name. We do not want to be comparing ID numbers against each other, right? Does that make sense? They mean nothing to us. So we're going to drop that column. Drop ID. Just like that's our patient's table. No ID, please, because that was useless. But otherwise, we've got all these. These are numbers representing different pieces of an examination or like a test maybe of someone for breast cancer. And then class, I'm going to assume 0 means they did not have, let's see. Yeah, they did not have, like, maybe it was benign versus malignant breast cancer, something like that. So 0 versus 1 again, like was it bad? Was it an okay kind of breast cancer? And let's take a look at all the numbers that we've got as well. So patients, how many columns do we have? So 10. So if you subtract the class, that means you got points in a 9-dimensional space to compare against each other. And then how many rows do we have? Patients, not rows. We've got 683 things. All right. How many were class 0? How many were class 1? What kind of, I think it's probably, yeah, probably malignant versus, or like a certain kind of breast cancer versus not a certain kind of breast cancer, something like that. Let's group them by the class, see how many we've got, because by default it's doing a count. So it looks like class 0, maybe benign breast cancer was 444, and class 1, let's assume that's maybe like malignant, something not good, was we got 239 patients with that, and so we've got data on all of them. And notice that all these numbers, they're like whole numbers. It's like not anything with, like there was a cutoff somewhere, it was rounded. And so when you go and try to explore this data, that's the first thing I want to show you. We're still doing that part together. When you go try to explore this data and do like a scatter plot, something weird is going to happen. Let's do that, and we'll group by class. Again, as we were doing, but if we do, I guess, bland chromatin, however you say that, versus single epithelial cell size, you'll notice something. There are hundreds of points here, right? 600 points here, but I only see about maybe 50. So there's a bunch of things that are right on top of each other. Does that make sense? That is not helpful when we're trying to visualize things. It is trying to color it, kind of like it's more between yellow and blue. That's more blue, but sometimes yellow. You can kind of see it, but it's not very helpful. So, that's a bunch of dots overlapping. This is called overplotting. We're plotting things over each other. That's kind of disgusting. And so a cool thing that you can do that I'll just show you really quick. You don't need to understand it. I can barely code it up, but let's go to data 8, practice, chapter 17. Let me just show you something you can do, and then I'll have you try things. Randomize, column this. Here's something cool that you could do to solve this problem. Oops, did not copy. There you go. Let me do it, and then I'll try to explain it. I honestly don't know why they chose 0.9 there. So let's try to change it to like 0.1. Surely that's fine. Boop. Here's something that the textbook recommends. If you ever have overplotting going on, what you can do is you can take all your data, and you know it's overlapping, like those are the real values. You can nudge each point randomly using a normal distribution. Like for this, take a point that was here, you nudge it and the bland chromatin amount by a certain amount, and using a normal distribution, you do the same for the single epithelial cell size amount. Like you're shifting the x's and y's by a random slight amount. It's like you're jittering the data. And then you can kind of see them all next to each other finally, because like some have been moved randomly in different places. So like these were the actual values that were all there, but they've been like spread out, so you can see like how many yellows were there versus how many blues. That's kind of nice. So it's like a jittered kind of table. And so what they did was you made this function called randomize a column value, which is like take the original value and add a random amount to it. Like take the original column and add a random amount to it, where the mean of that random number was 0, the standard deviation was 0.1, and get that many like offsets, as many things as there were in the column. Take the length, like it's going to generate a long array of things. It's going to add that to the table. It's like it's going to take the original column, give back a new column with that data plus a random offset for every value around 0. So sometimes it subtracts, sometimes it adds with a standard deviation of 0.1, take from a normal distribution. So it's changed, like nudged all the values, nudged the x's a little bit that way, a little bit that way. It's like close to where they were though. And so now you can actually see everything. So that's just showing you again that like, okay, these two things, they kind of correlate. Well, like you can kind of draw a line, but there's going to be some overlap. So maybe we should be using all the things at once. All right. So that's my question to you. We've got a bunch of functions. Go and press play on them so that we have them all. See if you can figure out which ones to use. But here is our breast cancer table. We would like to split it up. We'd like to do exactly this process. We would like to split it up into a training set and a test set. We'd like to evaluate how well the training set predicted every value in the test set. All right, so let me write that down. So that's what I want you to try for this patients table. So shuffle the patients table, because you want to do a random test set and a random training set. Right? Shuffle the patients table. See if you can apply everything we've done, because it's been a lot, right? Let's do like a 50-50 split, or as close as you can to a 50-50 split for the training/test sets. And evaluate a 5 NN classifier. See how well 5 nearest neighbors classifier with k equal 5 works. And if you finish early, you can try k equals 3, k equals 1, k equals 7, see how it compares. But that's going to be the process. The first one is shuffle the table and do a split, and that was this. So we've got an example of that. It's just like, essentially, if this whole section evaluating the classifier's accuracy, you're going to kind of go through that and do what we did, but we've made some nice helpful functions for ourselves, haven't we, that you can call. So it shouldn't be too much work, but just like remember what's going on, remember the names of everything, call them yourself, see if you can get it working. Okay? Questions about the question? Yeah, go try that for a few minutes, and then I'll do it too, and that's a good place to stop for today. It's definitely a 3-lecture kind of chapter. All the good stuff we did today in the code class. Any other lecture, put it along at the top of it. The modules or find them. Chapter 17. And then here, if you wanted the new stuff as well, everything that I've done up to now, just like let me really quickly give it to you. So if you refresh the page, you now have everything that I did as well. Just now, if you wanted like the name of the table, which CSV file was it in, if you didn't take that down. Let me know if you have any questions. So it should just be like, you follow the process of doing the split, figure out the right number. And we've got a nice function that kind of does it all for us, but feel free to play around. All right, my timer is about to go off. Were there any questions as we were trying that? The magic name of the final function we need is going to be that evaluate accuracy function. Just like make the split and it'll do the rest for you. But if you want to predict somebody new, then you'd have to maybe do a little bit of extra work. Try one of the intermediate functions that we called using evaluate accuracy, right? Call KNN, something like that. But let me show that to you, and we'll go from there. So let's do, first we gotta shuffle the patience table. So it's called patience. I want to shuffle it by taking a sample of exactly as many things as were in the table. You can just say with replacement equals false if you want to, but if you want to be very specific about it, like I want all 600 and whatever things, 683 things, 683 with replacement equals false. That can be our shuffled patience. And then I want to take half and half as best as I can. So I'm going to copy and paste this idea because it's going to be the same idea. Training set and test set become these guys. It's going to be shuffled patience, not shuffled line. And then what's 683 over 2? It's not going to be even, is it? So like maybe we can say that the test set is a one bigger than the, or sorry, the training set is one bigger than the test set. Either way is fine. But we got to go up to, let's say, 342 for the first one. It's one longer. And then from 342 to 682, so just like put 683 there again, that will split it as best as it can in half. Does that make sense? So training set's one longer. And then after you've done that, you can call evaluate accuracy. What does it take? Do our question mark. It took three things, right? Training, test, and K. So you give it our training set, you give it our test set, and you give it a k value, and I said, let's try to use 5. It's going to take a second. But it looks like we get some very good accuracy of was it, I guess, benign cancer or malignant cancer, something like that. Or was it a certain kind of breast cancer versus another certain kind of breast cancer? But it looks like with decent over 95% accuracy for this what's it called? This split at least. If you resplit it, it might be even better, a better predictor, a worse predictor, because it was a random shuffle. Well, this time it was 98%, amazing. So that could be due to the training set having better things or the test set having easier things to guess. I don't know. Either way. But yeah, you can play around with that. You can play around with like K values, like 3, was 3 better? Was it worse? Fewer things to compare against. That's only 97 versus 98. 7. More things to compare against. Is it going to find a better value? 98.2 versus, it was 5. Still not probably the same, I think. So yeah, that just goes to show that you can do really, really well with k-nearest neighbor. That is a decent machine learning algorithm to do classification. So that's why we're learning it. It's a good first one to learn. And I think that's a good stopping point for today. Are there any questions about any of that? You see how we do it? So definitely go back and study these functions and how we built them up. Like evaluate accuracy is calling so many things deep down, right? It's calling our KNN function, and our KNN function was calling a million other things, right? KNN was doing so many things for us. It did the find the nearest neighbors, find the distances, give me all those distances, take the majority, right? It did those things. It did the nearest and get the majority. So what was nearest? Nearest found all the distances, it attached them, sorted them, and just like it all goes down, right? That one called all distances, which found for a new row, the distance from that to all the training data that you passed along there. Just like it's a bunch of different helpers all the way down, and they all work together to give us what we need for k-nearest neighbors. It's really nice, really cool. But I think that is a good place to stop. So we only technically got like 2.5 slides done, didn't we? Because we were working on this one, then we did these 2. And then there's not too much left in terms of actual content, but that's a good second place to stop for the day. I think a lot of just like practice and making sure we understand it, because we finally got it done. We finally got k-nearest neighbors done, and that's the main classification algorithm for. It's the only classification algorithm for this chapter. There's another regression algorithm that we'll talk about later, though. Okay, so I think that's a good place to stop the recording, at least.